Curvilinear coordinate systems 5 performed line integral over the contour dr dot e theta hat, where e theta hat is a spherical basis vector and c is the quarter circle of unit radius lying in one quadrant of the Cartesian xz plane shown below. We have already evaluated it in using Cartesian coordinates and spherical coordinates. Now we will do cylindrical coordinates. And we're going to ask what happens to the value of the integral if the direction along C is reversed. Now, in cylindrical coordinates, I have to write the displacement vector. So these are the cylindrical coordinates, rho, phi, and z. So you can see that if I change rho by a small amount d rho, I will go on this axis in e rho hat direction. If I change phi by a small amount in e phi hat direction, I will go on this circular arc by rho d phi, and on the z axis I will go by dz. And in this problem, along the contour that we have to consider, phi is equal to 0 degrees. All right, so we have phi is equal to 0 degrees, so we're on the xz plane. All right, and as you can see, rho is going to be kept at 1 here, so rho is going to be equal to x actually. So dr vector, now I have determined, is d rho in e rho hat direction plus rho d phi in e phi hat direction, and I have dz in ez hat direction. So this is generally true, but here I have phi is equal to 0 on this path because I'm on the xz plane. So I have d phi is equal to 0 as well. Therefore, in this particular case, my displacement vector dr becomes d rho in e rho hat direction plus dz in ez hat direction. A general position vector is given in terms of cylindrical coordinates, rho cosine phi in ex hat direction plus rho sine phi in ey hat direction, and then we have z in ez hat direction. That's identical in cylindrical coordinates, and therefore with phi is equal to 0, this is going to become rho in ex hat direction and z in ez hat direction. Now this position vector is also equal to, using Cartesian coordinates, x ex hat plus z ez hat, and y is equal to 0, remember. So we can write e rho hat using this. E rho hat direction is the derivative of the position vector r with respect to rho divided by the magnitude of this vector. Now the magnitude is square, it's going to be so first I have to take the derivative with respect to rho. I'm going to obtain there's no rho here, ex hat. So the magnitude of ex hat is equal to 1. So this is divided by 1, and therefore this is just going to be equal to ex hat. Actually, I have found out that rho cosine phi, well, phi is equal to 0, so x is going to be equal to rho here. And therefore, I also have square root of rho square plus z square is equal to 1. This is true on this contour C. Okay, so I have found out that e rho hat is identical to ex hat on this path. E theta hat, let's remember what e theta hat was. E theta hat using Cartesian coordinates was z ex hat minus x ez hat. So it is z, but ex hat is equal to e rho hat minus x. X is rho cosine phi in ez hat direction, but we also know that phi is equal to 0. So this is basically equal to 1 because phi is equal to 0 degrees on this contour. All right, so we can write dr dot product with e theta hat now. Whereas our displacement vector is here, d rho e rho hat dot product with z e rho hat. This is going to give us z d rho. And then we have dz ez hat dot product with minus rho ez hat. So it's going to give us minus rho dz using the cylindrical coordinates. Now we have to perform this integral. So let me rewrite here. I have e theta hat is z e rho hat minus rho ez hat. And my displacement vector dr is d rho e rho hat. And I have plus dz ez hat for the displacement vector. So let's just keep that in mind when phi is equal to 0 degrees. Okay, now we're ready to perform the integral. The integral of z d rho minus rho dz. And I also note that I have, since rho square plus z square is equal to 1 on this path, I can write wherever I see z square root of 1 minus rho square. And wherever I see rho, I could also write square root of 1 minus z square. All right. So with that, my contour integral dr dot e theta hat becomes, let's take a look. Dr dot e theta hat is z d rho, but z is square root of 1 minus rho square. So we can write this as integral square root 1 minus rho square d rho. And then the next term is minus rho dz. And for rho, I can write square root of 1 minus z square dz. And how do I change rho on this integral? Remember that I have found out that rho is equal to x on this path, on this contour C. So x has to go from 1 to 0 and z has to go from 0 to 1. Therefore, rho has to go from 1 to 0 and z has to go from 0 to 1. Now I have a situation identical to what I had using the Cartesian coordinates. The contour integral dr dot e theta hat becomes minus twice the integral from 0 to 1. So I'm changing the rho to z here because it's a dummy variable, integration variable. And then I change the integration limit, so I have a minus sign here. This becomes minus twice the integral square root of 1 minus z square dz. Now, do I know the answer to this integral? minus 2 integral 0 to 1 square root 1 minus x squared dx, that integral is minus pi over 2. So therefore, I know the answer to this integral as well. This is going to be equal to minus pi over 2. So this will be the answer. Okay? And this is as shown in the star equation, which is this equation here. This gives us minus pi over 2 as the answer. So we have obtained exactly the same answer. And if we change the direction of the contour, what will happen? What happens to the value of the integral? We would have to change the limits of this integration, and this would give a plus sign here. So if we change, if we reverse the direction of our contour along C, the sign of the answer will be positive. So that means we're going to have plus pi over 2 as our answer. Okay, so in this part we have talked about doing the same integral dr dot e theta hat on this contour on the xz plane going from x equals 1 to z is equal to 1 on this unit circle. First, I have written the position vector rho cosine phi ex hat plus rho sine phi ey hat plus z ez hat. On the xz plane, phi is equal to 0, so I have rho ex hat plus z ez hat, which is also equal to x ex hat plus z ez hat, because y is equal to 0 on this contour. So I note that rho must be equal to x on this contour. Therefore, E rho hat is also equal to Ex hat. The displacement vector dr is going to be d rho E rho hat plus dz Ez hat plus rho d phi E phi hat using cylindrical coordinates, but d phi is equal to 0. And E theta hat, which I have shown to be equal to zx hat minus x Ez hat, is z e rho hat minus x, which is minus rho ez hat. So I have obtained e theta hat and I have obtained dr. So I take the dot product. These are orthonormal unit vectors, basis vectors. So this is z d rho minus rho dz is the dot product. Z d rho minus rho dz. Z is square root 1 minus rho square. So square root 1 minus rho square d rho, and rho dz square root 1 minus c square dz. But x has to go from 1 to 0 and z has to go from 0 to 1 because rho must be equal to x on this contour. Okay, so this becomes minus the integral 0 to 1 square root of 1 minus rho square d rho, or square root 1 minus z square dz. So it's the identical integral I have obtained in the Cartesian coordinates calculation here. And that integral I have shown to be equal to minus pi over 2. Therefore, this is minus pi over 2. If I reverse the direction along C, if I don't go from x equals 1 to z equals 1, but I go from z equals 1 to x equals 1, then I will be reversing the limits of the integration, and this will become plus pi over 2.